All right, welcome everyone to this new episode of Neural IR Talks. As usual, my name is Sergi Castella, analyst at Zeta Alpha, and with me I have my usual co-host.
I'm Andrew Yates, assistant professor here at UFA.
And today we're here to talk about this paper titled Task-Aware Retrieval with Instructions from Akari Asai and colleagues, a collaboration from a bunch of institutions, Meta, University of Washington, ENSPSL University, and INRIA, Allen Institute for AI, and University College London. Do you want to have a couple words on why we chose this paper and a bit of a high-level summary of what they do?
Yeah, so it's an interesting paper. I mean, they get good results. That's one reason to look at it. But it also kind of builds upon some of the other work we looked at, like Promptigator, where they get better results through better specifying their task and how it relates to the specific data they're retrieving. Mm-hmm. So the general idea here is they'll give some instructions describing exactly what they want to retrieve. So rather than searching for, I don't know, batch norm and expecting you get Python back or some, description of batch norm, you search for batch norm and you say, I would like Python code, or, I'd like to find people rephrasing this in similar ways, or I'd like to find, an explanation of what batch norm is, right? So it's adding this kind of level of detail that was missing before.
So you'd say that it kind of also fits pretty well into this kind of broader narrative that I think we've been highlighting a lot, which is this whole idea of zero-shot transfer or like robustness in information retrieval, right? Where you want to have neural retrievers that are good in domains that they were not trained in.
Yeah, exactly. So this paper will not add in new training data for the domains. So for example, we looked at nparse, which is generating new synthetic data given a domain. This paper doesn't add in new training data, but it tries to specialize to domains in a zero-shot way by providing these instructions. So a better idea of what is in the corpus and what should be retrieved.
Cool. And another thing that I think before we dive in, we can highlight is the difference between, if you read the abstract, you're going to see that they present BERRI and TART. Can we quickly differentiate between those two things?
Yeah, so TART is the model itself. It's the task-aware retrieval model. BERRI is this instructions coupled with existing data sets. So they basically produced instructions for a lot of benchmark data sets, BEIR, for example. So things like, retrieve a Wikipedia passage that answers this question, right? Or retrieve another question with the same meaning as this question. That's how. So you can imagine taking a Stack Overflow or a Quora data set and augmenting it with an instruction to retrieve a similar question.
Instead of an answer to the question,
exactly.
Right? So you can kind of adapt to very kind of, information retrieval tasks that are not so close to the classical kind of retrieval document. But what was that data set? I forgot the name. That was looking for counter arguments.
So there's Arguana. I think it's this one in BEIR. Yeah, exactly. So this already exists kind of in the data. It's just not made explicit. So here they're adding in the instructions to say, this data set's looking for a counter argument. Not any evidence either way for this argument, that sort of thing. Cool. So it's making the nuances a bit more obvious.
And finally, there's this kind of X-squared, I think we're going to describe a bit more in detail what this means, but there's this also X-squared retrieval evaluation, which is kind of like a new kind of...
Yeah, their idea here is kind of just to concat all the corpuses into a single task.
Yeah. And see, we're going to see how, what do you think, how relevant do you think that is in terms of evaluation?
Yeah, it's an interesting idea. I think there's some trade-offs, but we'll get to that, I suppose.
All right. That said, I think we should dive into a bit of the background and then, the task formulation, data sets, evaluation as usual. So maybe we can start by discussing a little bit the background section of this paper, right? One we've already mentioned is this whole aspect of recent works in zero-shot training of retrievers or domain adaptation, right? So in this paper, they highlight that there's kind of three main kind of flavors or ways that people have been trying to do that so far, which is first the self-supervised approaches, like the contriver that I think we did one podcast episode. It was not the contriver, but it was, I think, the...
Might have been co-condenser. I may be misremembering now. Spider. It was definitely, yeah. Spider.
That's one. Others that do supervised on MS Marco and then transfer, right? Like Mono T5. And then finally, the one we did the last episode on in parse propagator, which is this whole area of generating synthetic data and training on that. Is there anything you'd like you'd kind of add to those three flavors of?
No, I think it's a good overview. Maybe two things to point out. Training on MS Marco and then transferring works pretty well, especially with the cross-encoder. Like you mentioned, Mono T5. We'll see in this paper this paper outperforms it a bit, but it still works really well and it's competitive.
I feel like that was also one of my kind of highlights or something that I feel is a little bit disappointing of these new methods.
It's just hard to beat, I think. It's a strong baseline.
Still very hard. Cool.
And then for this last family, so we talked a bit last time, but there's Promptogator, which has some information about the task. It's kind of analogous to this. And then there's like the mParse work where you just see the documents. So there's a little bit of difference between methods in this.
So your point would be like Promptogator would have some sort of implicit task awareness by adding the examples of the specific task in the prompt
Yeah, I think so. And then this feels to me like it's going a bit further where it's structuring the idea of a task a little bit more. They break it down into a few things. I guess we'll get to that. And they kind of use it they break it down and try to use this description. So it feels to me like not extending, but going in that direction a bit more, the Promptogator direction. Okay. Whereas other approaches like Spider or the mParse try to remain unsupervised, right?
Totally. That's a good point that I feel like I overlooked often, like this idea of different tasks in IR and how you kind of inject that type of information in training. All right, so the second, I think, very important background concept is this concept of instruction tuning, right? If I'm correct, the first kind of people who proposed this, or at least popularized, was this paper from Google called FLAN, where they basically, as a kind of extra step in the training of a language model, after like a static pre-training with the corpus of self-supervised data, you kind of convert a data set into some NLP, so natural language instructions, right? And you fine-tune on that. I don't know, is there anything like you'd like to add to how that?
Yeah, this is more or less the level that I understand that. So I think they're performing fine-tuning with additional instructions in the prompt is generally the idea here. So different than like the RLHF, the reinforcement learning with human feedback. We've seen, even though there's some overlap, I guess.
Yeah, I guess there's some overlap, but it's a bit kind of unfortunate that the names are. I think that the paper that was around a year old from OpenAI that used RLHF was called InstructGPT, or like the model they present is called InstructGPT, which is kind of very close to instruction tuning, but it's a different thing. And then there was this paper that scaled this instruction fine tuning on thousands of data sets. I think it was called FLAN. And they show how you can apply this to encoder, decoder, or decoder only. I think it was published on iClear last year. So I think that's a kind of like, that's part of the sort of big recipe for training these massive language models. That's kind of one of the things. And I feel like this paper is kind of like incorporating that into in a kind of smart way into the information retrieval space.
Yeah.
All right. And finally, there's some, so in the background section, they introduced some kind of retrieval with the descriptions kind of background work. I wasn't aware that had been a thing, or like, do you think is there anything interesting to highlight in terms of what people had tried?
Yeah,
here?
Maybe not for this paper specifically, but in general, they kind of hint at this. So some of these old data sets had different forms of query, like keyword query, description query, so natural language, sometimes even a narrative query, which is kind of the assessor, exactly what they're looking for. So you have a clear description of why this was judged. Where
you have, in this data set, you'd have an explicit kind of description, like...
Yeah, like relevant document should include X or Y or Z and B, or, some combination of information, right? So you're looking for this specific thing in some context. And so the narrative would make that really clear. And this is almost like an instruction. So
in these data sets, but it has never been something that it's a kind of a free form kind of description. Are you kind of do you mean that some datasets provide some type of classification of what queries are expected to?
They provide alternate forms of a query. So Robusta for older data set is a good example of this. So you have black bear attacks, or you have a description. This isn't word for word as the query is from the data set. Something like, I'm looking for information about black bears attacking humans.
Okay.
Right. So this is a little more specific. And then you have a narrative where maybe it requires this to be in the wild. It's not a zookeeper incident sort of thing. Mm-hmm. A little bit more of the minutiae there. Right. Okay. So just a description of what it would mean for a black bear attack to be relevant to this specific information need. Okay. So you can think of the original keyword query as underspecified, and this is adding additional details that are actually there in the relevance judgments. It's just not clear from those 3 keywords, black bear attacks.
I see.
And then previously, these longer queries, so these narratives or these descriptions, tended to not work as well as the keyword queries before neural models. And so one difference we've seen is like BERT-based methods, other neural methods, do much better, or often do much better with these longer queries, the natural language ones, than they would with just the keywords. Mm-hmm. So, part of that could be extra information coming in. Part of it could be it's in the natural language form, such like most of their training data. So it's a bit closer to what they naturally expect. So use a lot of quotes.
Yeah, I see. And I guess that's why in the old days, people used to say, only put the keywords in Google. You're going to get better results than if you ask the full thing, which is something that certainly changes, right?
Yeah. And you saw this with things like BM25.
Yeah. Cool. So now let's go a bit more in detail into what retrieval with instructions means, basically. So I think that figure 1 has a pretty nice kind of overview of what this means. Can we maybe go through it?
Yeah. So I like this example. So we have a query implementing batch normalization in Python. And so using their ideas or their versions of user intents, this could be things like you're looking for Python code. That's one intent. You could be looking for other questions that are similar, right? Maybe this is part of a system where you want to show the user other questions that may have answered their question before they actually submit it. Like imagine you're going through a pipeline submitting this to Quora, right? They don't need to answer it if it's already answered.
Yeah, correct.
And then actually just looking for an answer, right? So these are all different reasonable things you could do given that query. And so these they view as intents here.
Yeah, implicit user intents.
Yeah. And so prior work, so Promptigator, for example, would handle this on a per data set basis, I suppose, which is what they show on the left here with normal retrieval, whereas they try to push these intents into the query rather than having the model learn it in some way. So rather than training separate models for each intent, they try to move it into the query with the same model. So rather than having a specific model for code, you add to the query, I'm looking for code, and here's the query associated with that, so that you know that what should be returned should be, Python code, rather than an answer.
So would you say that up until now, more or less, every information retrieval data set has sort of some fixed implicit user intent, or is at least kind of like built with some specific user intent from scratch? Because like if you have this question in a data set on MS Marco, what would you expect the sort of relevant document to be labeled? The top document to be.
This is interesting because there's also work looking at different intents on MS Marco. So actually intents are more of a hierarchy, and here we're looking at a very high level, like are you looking for code or for an answer or for a query, right? That's a very high level part of the hierarchy. If you imagine going way, way deeper where we're looking for answers, well, you could search for Facebook. You could have a navigational intent where you now want to be redirected back to the website. Or you could be searching for like history of Facebook. So this is some sort of, I don't know, right? So informational intent of not a factoid nature, but some other nature, right? So there's not a single set of intents. So this work is, I think, looking at higher level intents in a way that previous work usually has not.
Okay.
Though maybe work has focused on very specific, like navigational intent versus informational. Like, should I send someone to this website or should I return a Wikipedia page about this website sort of thing?
So normally, like, that's not something that is baked in most benchmarks or like it just kind of, you assume implicitly that the annotators will kind of assume the correct intent, and then that's...
Yeah, so I guess one way to say it is there's a high-level intent that's baked in with the benchmark. So with MS Marco, you're always looking for some passage answering the question in some way.
Okay.
Could answer it in 2 words, could answer it in 3 sentences, but it's a passage answering the question. So that's like the high-level intent that's fixed. And then there are a lot of low-level intents, like whether you're looking for, that navigational page, or you're looking for a short answer or something else. And these usually exist, but they're not necessarily annotated or made explicit. It depends on the data. So it usually happens, I guess, implicitly at this really detailed level. Whereas the high-level intents, so here you're looking for an answer. I guess that's normally fixed with the data set. So MS Marco doesn't include, finding a duplicate query and also finding an answer to the query.
So if I'm understanding correctly, the idea of this paper is to sort of augment existing data sets with explicit annotations of user intents, so that then the model can kind of like learn about that also. Besides the hope would be if you kind of train a model saying, okay, I want to retrieve code. It's going to retrieve code. I want to retrieve an answer, right? I want to retrieve an implementation. If you train on all these sets of instructions, eventually if you test it on an instruction that it hasn't seen, it will somehow generalize to that one. And it will somehow kind of like be able to do zero-shot new task. So is this kind of the hope, or like is this somehow, do you think this is the motivation, or do you think it's basically to kind of like have better performance in the tasks that it has that you train on, basically? Like,
I mean, I think the hope is to move to being able to use the zero-shot property of these models to deal with tasks we haven't seen. But I suppose that's not really being evaluated here because there's no leaving tasks out as far as I understand. But you can imagine that tasks probably have a lot of overlap between data sets, right? There are only so many tasks, many common tasks. So I think it's kind of taking that and moving it into the query as a way to improve zero-shot performance, because you don't need a task-specific model anymore, but you're still handling some part of the task. So you can do better on these data sets without specializing to each data set, I guess is the idea.
Yeah.
Where specializing doesn't necessarily mean training, but it means having a model trained on examples and instructions specific from this data set, maybe.
Yeah, so I guess we can go into BERRI, which is this benchmark, bank of explicit retrieval instructions, right? And kind of go through the what data sets, what data is included, and a couple of examples of queries for that. Sorry, a couple of examples of like data points.
Yeah. So BERRI, they call it. It consists of different tasks. Each task has some queries and some instructions. So the instructions, they break down into intent, domain, and unit. Mm-hmm. So intent are the high-level things we've been looking at, like code versus answer. Domain is sort of like, is your answer coming from Wikipedia? Is it coming from PubMed, like a medical corpus somewhere else? And then unit is a bit odd, but it's the unit of retrieval. So are you looking for a sentence? Are you looking for a paragraph? This sort of thing. I only say it's a bit odd because these models don't have the capability to change the unit of retrieval. So it's not that my question could be answered in a sentence or a passage. It's more that this question is tied to a data set that was indexed at the sentence level. So look for sentences, don't find passages.
Yeah, cool. So I think I wanted to look at what are some good instructions. I think that the table one maybe has some nice examples of what you just said, right?
Yeah, so the top example you see, retrieve a Wikipedia, that's the domain, paragraph is the unit, answers this question is the intent. The second one is like a summarization intent, so it's looking for a simplified paragraph. Again, the unit's still paragraph, domain is different, now it's medical paper.
So maybe one of the, like we've mentioned before, one of the most interesting ones is this arguano, right? Because it kind of differs a lot from a lot of common retrieval tasks, which is this retrieve a paragraph from an argument website that argues against the following argument.
Yeah, so here the task is very specific, right? It's against, not supports.
Okay, so if we look at how this is implemented, I think this is basically figure 2, right? That goes over the data sets and domains and tasks that are gathered. Is it simply a thing of like prepending this into the query, prepending these instructions that we have seen into the query, and just like feeding that as a new query?
Yeah, that's exactly what they do. So treat it as a large data set. Each query now gets the task from that data set. Right, okay. So argue-n gets this retrieve the counter argument task instruction we just saw. So
they just prepend that, or concatenate basically that instruction and query, and then that's kind of whatever you feed into the bi-encoder or cross-encoder. Right?
Yeah, that's it.
Do they have one instruction per data set, or do they have some sort of like way of combining multiple ones?
I believe they only have one instruction per data set. It would be a lot of work, I think, to look at specific queries and try to, classify them into some lower level intent hierarchy.
Yeah, I guess I was just like curious to know whether like that having only one way of expressing intent could hurt in terms of kind of like over specializing on like that specific phrasing or something like that, and then if you like hurting performance if you rephrase the instruction in a different just sentence or.
Yeah, that's possible. I believe they came up with extra instructions and chose some subset, but I'm actually not sure what they did to choose from those.
All right. So now when it comes to the data sets that they include in this, because this is basically like a conglomerate of a lot of data sets augmented with these instructions, right? So what do you think are interesting choices in this data set collection, or like what is the rationale between them? Is there anything you're missing? What is interesting there?
Yeah, no, I think it looks like a reasonable set. I mean, so they look from several different sources of data, like Kilt. Some stuff, Sentence Transformers has identified their own searches. They, include a lot that we've seen before. So it looks like they cover, have a reasonable coverage. One interesting thing is they talk about repurposing non-retrieval data sets. Okay. And some of this is also done in things like BEIR, like duplicated questions, right? But here, this is not necessarily retrieval. It could be classification, where you're trying to decide if this is a duplicate of another query or not.
Yeah.
Or summarization, for example. So maybe you somehow have generated many different summaries, and so you're trying to retrieve the best summary for your text.
Okay.
How realistic this is, I guess, depends on a lot of details. With summarization, I guess it makes sense if you have some way to generate summaries. Maybe they're even human-generated, and you want to pick the best.
No, that's quite interesting. And I mean, I guess it makes sense that you need to kind of, if you want to have a broad scope of task or intent, user intents, you kind of have to go outside of the classical information retrieval tasks, and then you get all of these sort of like paraphrasing or like finding the summaries or something like that are kind of more diverse.
They also did some checking to make sure that these repurposed data sets could work. So they said, for example, they looked at the queries to make sure they're actually self-contained. And I guess they went from about 60 data sets, more than 60, they say, to 37. So after this filtering. So you can imagine a summary is not the best example, but just a really brief summary where it's not clear what this connects to.
Yeah. Okay. And how do they do this filtering, or like, I guess it's basically, does the task make sense in an information retrieval setting, right?
Yeah, like exactly. Really? They just looked at 20 samples from each to see if it if it makes sense in information retrieval setting.
And then basically like as a human, it's like, this makes sense, this doesn't make sense, or like this should be doable, this should not. Right?
Yeah. Okay. Exactly. So they give the example of review text, like, I love this, as a review title is underspecified. You would not know what to match that review title to, right? It could be any sort of thing.
I think that's a perfect example, amazing. Okay, and then I think that the last thing about the data that is interesting to highlight is negative document, right? They do provide a selection of negative documents. So can you kind of explain that a bit more in depth?
Yeah, they try to do this in two ways. So first they use, at this point, I guess, standard hard negative selection, basically finding negative documents that are ranked higher than they should be for some value of should by another model. So finding, documents the other model mixes up. They start doing this using mini-LM. Later they switch, I believe, to TART or Contriever. So they switch to TART in order to do distillation from their cross encoder to the dual encoder. So they basically this is maybe getting ahead of things, but they have a
Yeah.
cross encoder that tends to work better. So they say, well, why not use the cross encoder's judgments of what's positive and negative as our hard negatives rather than some other model that's not as good at distinguishing them.
Okay.
And then they have another strategy.
No, I was trying to understand properly this. So, like, I'm guessing that some of the tasks in this collection of data sets already have negatives, or are all of them don't have negative?
It depends on the data set. So some certainly have negatives, maybe some don't, but typically you would at least know some subset of the negatives, right? But usually 99.9% of the corpus is negative, for any query.
Yeah. But normally they provide, like in MSMark or these data sets often provide triplets of like query, positive, and a negative. Like hopefully negative is interesting in some way, right?
Yeah.
And here, what they're doing is they're using this mini LM, which is a re-ranker.
This is a cross encoder, yeah.
A cross encoder, okay.
A re-ranker, yeah.
To get some of these top documents, and then they just select the kind of like the second non-labeled most, or
so I don't know exactly what they're normalizing, but they have some score threshold where they look at the results from the cross encoder and then they compare the score threshold and they add it as a negative if it satisfies it. So the intuition is exactly what you described, right? This was ranked 2, but it's marked negative. Let's use that rather than the negative we had that was marked, position 500.
Okay. I guess what I was trying also to understand is whether this was a kind of highly if a lot of humans are involved in annotating these hard negative, or if it's just like a kind of process of mining them automatically.
Right. It should be fully automated. So you're training a model, but there's no new judgments happening, right? It's only used to train the model.
Okay. Yeah. Okay. But these negatives are included in the sort of in the BERRI bank of benchmarks, basically. So it's not just an artifact of how they train their model. It's something that is included in their sort of BERRI bank of explicit retrieval instructions.
I believe they're included in the data set.
Okay.
Yeah.
Cool. I think that kind of should give more or less. No, wait. Sorry.
There's also the unfollowing negatives.
Yeah, exactly.
Which is basically just remove the instructions and see what's retrieved. So I believe they use contriever here. So it's kind of, if you didn't have any information about the task, what would you retrieve? So you can imagine it as a negative intended to get the model to use the task instructions better.
Yeah, exactly. Cool. Okay, I think that's enough for the dataset parts, and now we can move on to the modeling, or like their model, basically, that TART, which they basically have both a dual encoder and a cross encoder. Maybe you can give an overview of that.
Yeah, so as before, they have a dual encoder or bi-encoder. This is doing dense retrieval, right? You process query and document separately, create a vector, approximate nearest neighbor search, gives you the closest document vectors to your query vector. This is as we've talked about before. What's new is that they're concatenating the task and the query here. So when you have a query input, it also contains the task along with it.
Okay.
Documents, they don't concatenate the task with, of course. That would kind of break their setup. Because in theory, a document should work for multiple tasks.
I see. Yeah, I see what you mean.
Even if in the valuation data, I don't know if it works out that, but in theory, a Wikipedia page can be used in many different ways.
I see.
And then a cross encoder is just a standard re-ranking cross encoder. So they take the task, the query, and the document as input all at once.
I see. So then, I guess it's so like, what is it? What is special about this training setup, such that it deserves its own name, kind of?
I think the name comes from the instructions. So I think once you include the instructions, there's not anything new happening here.
Okay.
But that's what they intend, right? So they're instructions with a bi-encoder, instructions with a cross encoder.
Okay.
Though the one difference is this knowledge distillation. So that is done. Right. That has been done. It's just that what they're doing is using it from one of their models to the other. So they're distilling from their cross encoder with instructions to their bi-encoder with instructions. And by distilling...
Right. So maybe it's useful if we just kind of go through the steps of training this. So basically, you would have for the bioencoder, you'd have some contrastive learning with in-batch negatives, right? But they also mix in some of the hard negatives during this training, right? So then you have a trained dual encoder, and then for the cross encoder, you train it exactly like the same, right? Basically, you just use these positive and negatives data. And after that, you have this distillation you were mentioning, right? To get the dual encoder to perform better than it was.
Yeah, and I find distillation to be a bit of a confusing word here, because really all it means is you're selecting hard negatives with a different model.
Okay.
So rather than using a mini-LM re-ranker to pick hard negatives, they're using the TART re-ranker to pick hard negatives.
Yeah.
And TART is better because it knows about the instructions, and so it should be able to pick even harder negatives than the model that didn't know about the instructions.
Right.
I guess that's the
No, yeah, because
reasoning.
I guess that was what was confusing to me a little bit, because in my head, distillation kind of was basically using kind of the output of a larger model and kind of like trying to copy the scores after the softmax type of thing, right, by a smaller model, which has a kind of richer training signal, I guess. But in this case, it's not like you're trying to emulate the scores from the cross encoder, right? It's simply these mining negatives.
Yeah, as far as I understand from this, it's not mimicking the scores. There are things like margin MSE where you try to mimic the difference in scores, right? So the cross encoder, they were this close with the cross encoder, so they should be this close with the bioencoder.
Okay.
Or you can imagine like the amount of the score given to each of the top 10 documents. So it's like 50% to document 1 or 20%. So you can imagine like the score distribution over a list.
Okay.
But as far as I got, that's not what they're doing here.
But that is something that has been, like you said, some have proposed.
Yeah, so margin MSE, for example,
margin
is
MSE,
a commonly used technique, the first example I mentioned.
Okay. Right, so in the experiment section, they have this interesting differentiation, right, between what they call zero shots and X squared evaluation. Can you sort of like give a sort of high-level overview of what that means? What was kind of like the evaluation philosophy kind of behind all of these? Basically?
So zero shot, I think, is fairly easy to follow. This is just BEIR, right? Some sort of generalization. You have a new data set that you haven't trained on. So we've seen this in previous papers.
So to clarify, BEIR data, all the BEIR data sets are not included in the BERRI pre-training data.
Yeah, so what they report on is a subset of BEIR and LOTTE. LOTTE is from the Colbert v2 paper. It's also intended to be like BEIR, a cross-domain, sort of generalization benchmark. So I guess they report on the intersection of BEIR and BERRI, because in the tables they show results on BEIR. So I guess they're releasing additional instructions that are not used in this table, is how I understand it. Because they don't report on BERRI exactly, I just realized. Yeah, so it's because BERRI is used only for training, and so there should not be overlap.
Right.
Yeah.
Right. So is that the reason why there's no why they don't train on? They don't report the full BEIR results.
I suppose so, right? So they have this BERRI, which is safe to train on, and they have BEIR, which is separate data they want to evaluate. Zero shot.
So that's the zero shot part of the evaluation, which I guess is kind of, like you said, pretty much the usual, like we've discussed in the past. And then there's this X squared retrieval evaluation. So what is X squared and why is it interesting?
Yeah, so this is combining different data sets, I guess, into a single data set is what they want to do. So they call it a pooled corpus. So for example, you take different tasks and combine all their documents, so you have a single corpus. They say this measures robustness more. Because you have additional documents you could think of as distractors, I suppose.
Yeah, okay.
If you assume they're not relevant.
Yeah.
The question I have is, are they really not relevant, though? It depends on the task and the query. If you add in all of Wikipedia, you've added in a lot of relevant documents for some of these tasks that may not be labeled at all.
Yeah.
So there's a trade-off there, I guess, with adding additional distractors or documents that are clearly not, that should just confuse the model, but also adding in documents that may actually answer some of the queries you have from some of the tasks.
So you basically make like a pool of everything in there. But I guess like for the tasks that are quite narrow, like, I don't know, like Stack Overflow or a lot of these data sets, these structures are probably not that kind of hard to dodge, or right? Or like, I guess that would be my kind of intuition.
Yeah, they shouldn't be. But I guess it could be that there's some robustness issues that are not uncovered if you don't have these, right?
I see. Do you? I mean, I guess that's interesting. The idea that at the data set, when or at least my understanding is of the data sets for information retrieval, the queries and the documents are sort of conceived together, right? Or usually you know the corpus, so you know what documents you have, and then you come up with queries given that. So your corpus is the entire internet, or your corpus is all of Wikipedia, or it could be many things. Yeah.
So, for example, some of the community question answering, your corpus could just be all the other queries that have been asked in the past.
All right. Do you like what is your sort of general sense of this X squared? Do you think this is something that is sort of like a superior way of evaluating retrieval models, and kind of community should move towards that, or do you think it's just a bit of a quirk in this context?
It seemed like an interesting idea that it's an interesting idea that I feel like is hard to know if it's better or not at this stage, right? So this question of how many relevant documents you're now adding, I think, is a big one. They argue that it's more realistic, and I think it is in some senses. But then also to go back to this unit of retrieval thing, well, it's not a totally real setting, because you can't actually retrieve a sentence from a Wikipedia passage or the whole passage unless you've indexed all of them separately. So realism-wise, it's...
Or unless I guess like the unit would make sense if you have a model that can discern, as in like, imagine you have like some ensemble of models that can do like abstractive question answering or augment or blah, blah, blah. And then there's some, in that context, it would make sense, right? I could imagine like a cross-encoder. So maybe you always index passages, and I could imagine a cross-encoder trying to narrow down the relevant span in that passage. Okay.
Something like that. But that would require, a bit more work to make that setting happen.
And a different setup. Yeah, exactly. Great. I think we've gone through these. Then there's just a couple of experimental quirks about byte sizes. I don't think that's... Well, maybe the only relevant thing, I guess, is like the rates of negatives and positive. They say that they have 5 sampled negatives per positive. 90% of the negatives are random and 10% are hard, either the regular hard negatives and or an instruction following.
1 out of 5 seems a bit low. Or actually, I don't know how you can get 90% with only 5, but because wouldn't you need 2 for?
That's a very good point. It's like basic ratios. Let me reread that.
I didn't see where that came from, actually. I forgot to ask.
Here at the end of page, section 4, the end of first paragraph, per GPU, the byte size is 16. Or maybe we can highlight it here. Per GPU, the byte size is 16. And for each positive document, we sample in total 5 negative passages.
6.4.
90% of them are randomly sampled from the corpus, and 10% are sampled either from the I guess it's just like the
I guess it's in aggregate.
It's in aggregate. Correct. So they just like have some like sampling strategy, and like 1 out of 10 times. Interesting. Okay, so I guess in aggregate it makes sense. You can have 1 out of 5 be 90% and break math. Okay.
Right.
All right. Let's move on to the results. Like, I guess the main results you can see in table 3, right? So as usual, maybe you can go through it for those only listening.
Yeah. So I guess we can. So first of all, these are results on BEIR. They're broken down by data set, and they also report the average. We'll probably focus on looking at the average. And so if we look at TART, the model from this paper, the very last group is TART in the dual encoder or bi-encoder configuration, and then 2 cross-encoder configurations. As in prior work, we see the cross-encoders outperforming the bi-encoder by quite a lot. So an average of about 37.4 versus an average of 44.1 for one cross-encoder, 44.8 for the other. Either way, you see that's a pretty large margin. So while we're looking at this cross-encoder, I think it's interesting to go back and compare to mono T5. So this is a really common zero-shot re-ranking cross-encoder we've talked about before. And there's not a huge difference, but there is a real difference, I guess I would say, between these, right? So mono T5 is 43.4. These methods, 44.1, 44.8. So their cross-encoder configuration is improving over mono T5 pretty clearly. So I suppose these instructions are helping with that. This mono T5 is also one of the strongest baselines. This SGPT, I believe this is also a cross-encoder, a very large cross-encoder, 7 billion parameters. Is slightly better on average than one of their models, slightly worse than the other.
Yeah. And then we have the first and the third. So I think you didn't mention this, but the table is sort of structured in sections, right? There's like the 3 sections of the baselines, which are, if I'm not mistaken, the first sections are like fully unsupervised models. The second is the MS Marco. So only pre-training on MS Marco? Is that correct?
Yes, I believe so.
And then the third one is the synthetic data camp. Right?
Right. And there's this cross that indicates cross encoders. So perhaps I was wrong about SGPT. It doesn't have this cross.
Sorry, can you repeat that? SGPT?
So they also have this cross indicating...
I see, yeah. Which indicates?
That indicates something as a cross encoder. I thought SGPT was, but it's not shown here, so I'm not sure what to say about that, actually.
Perhaps in the
yeah, they just referred to it without saying anything.
Indicates most unique cross encoder based ranking models. Yeah. I guess something that I would like to know your take on is, do you see any interesting sort of behavior when you compare on each of the data sets in BEIR, or like any surprise? Because I mean, I like the aggregate, like you said, is a little bit better, but it doesn't have that big of a difference. But I don't know. Is there anything else that you can relevant information that?
I mean, I think Promptigator is an interesting comparison because this is also using some sort of instruction for BEIR. I don't see a clear takeaway looking at individual data sets with Promptigator. Sometimes TART clearly wins, sometimes Promptigator does. But also their averages are somewhat similar if we compare the bi-encoder Promptigator and bi-encoder TART. Actually, somewhat similar is a little wrong. TART is a bit worse. So Promptigator is 44, TART is 37.4. And you see, individual data sets. So for example, NF Corpus is a bad example. Financial QA, TART is quite a bit worse, 33.7 versus 44. If we look elsewhere, like DBpedia, TART is a good bit better, 41.5 versus 36.4 for Promptigator. But as far as any specific trend to point out between these individual data sets, I don't see an obvious one. But I think that Promptigator comparison is interesting. And then if we look at the Promptigator cross-encoder versus the TART cross-encoder, we see the TART one is a bit better. For example, 43.9 Promptigator versus 44.1 or 44.8 with TART. So this training over all these data sets in their new collection, BERRI, seems to help a bit.
Yeah.
But it's still, in the somewhat comparable with Promptigator.
I guess something else that might be interesting to point out is the BM25 and MonoT5 re-ranker has a re-ranking pool of documents of 1,000 documents, right? Whereas this TART only has 100 and Promptigator has 200. What is normally the effect that this pool of re-ranking documents has on performance?
Yeah, I mean, it'll take a lot longer to re-rank. All right, it'll take 10 times as long to re-rank 1,000 versus 100 because these are essentially the documents that the cross-encoder has to score. I think the reason you see a bigger pool here is because it's using BM25 for first stage retrieval. And so you need to kind of try to deal with the missed documents that maybe dense retrieval would do better. Yeah.
Okay. So these ones would use a first stage dense retriever, which should have better recall. Is that, I guess, what you're
exactly? Yeah. So they use, I think, Contriever sometimes as a first stage retriever. That should have better recall, so you can get away with re-ranking fewer passages.
I see. And then in terms of, I guess it just feels to me like a very minor difference, but maybe there's something interesting there. It's the difference between the TART T0 and FLAN. So we have it here in section at the end of section 5.1. We explored different encoder only and encoder-decoder models to initialize our cross-encoder, right? We found that initializing TART full with encoders of T5-based instruction following pre-trained models, namely T0, 3 billion, and FLAN T5, empirically leads to superior performance as found in prior work. So they find that encoder, I find it a bit confusing what they're describing here.
I think they're saying that T0 is only an encoder stack and that FLAN T5 is this encoder-decoder stack. But they still take a vector and use it with this full this FFN in equation 2 to classify as relevant or not, rather than running the decoder stack and outputting something like relevance : true. So mono T5 would output like relevance : true, and then it would use the probability of that true token as opposed to the false token as its score.
I see.
So it does generation. They're stopping before the generation, so they're not running the decoders, and they're taking a vector from that encoder stack, so what corresponds to the first token, I guess, and using that vector to predict relevant or not. So like a classification head.
Oh, okay. That's a very interesting point. I didn't realize that there were the people would do things this differently. So in MonoT5, the way the relevance is calculated is by an extra true-false token on relevance, and then using the likelihood on that token as the relevance.
Yeah.
Getting the highest.
Yeah. So MonoT5 actually generates output.
I see.
Probability of generating true or false.
I see. Whereas here they have a classification head, binary classification head.
Right. They're not using any sort of decoder stack to generate output.
I see.
If they have one, like with the FLAN T5, they're stopping before that, doing classification head on top of a representation from the encoder.
I see. Okay. Is there anything else you'd like to? I mean, my general sense is, like you said, they do outperform their baselines. But I feel like there's, well, I don't know. Would you say this is kind of like enough proof to convince you that this is because of their task awareness sort of pre-training or training?
I think so. I would have rather had the exact same models trained as they trained them, but without the task as input. As baselines, I don't know that those appear exactly, but I buy that the increases shown here are probably attributable to the task-specific pre-training.
I guess that's a good point, right? It's not so much apples to apples in this case.
But I mean, it almost never is in settings like this, so it's not, But I guess this SGPT point I mentioned earlier, This is a bi-encoder using SGPT embeddings, not a cross-encoder. So I think it's interesting to see that with those GPT embeddings, the performance is about the same as with instruction tuning here. So with a much larger model with that SGPT, they get about the same performance as here with knowledge of the instructions.
Right.
But this SGPT has been, I think, fine-tuned on MS Marco because it's in the second group of
Correct.
MS Marco
Yeah.
models. So,
I see.
yeah.
But that's quite interesting. That is a bi-encoder.
Yeah, I thought it was a cross-encoder, but it is a bi-encoder.
In that sense, then this performance is quite good for a bi-encoder, right? Especially considering that this is a zero-shot. So this is a kind of like out-of-domain zero-shot evaluation where bi-encoders normally perform quite worse than.
Yeah, that's a really strong bi-encoder result. It's comparable with the TART cross-encoder.
Mm-hmm. Yeah, exactly. Interesting. All right, and then I guess the second part of the results is this X-squared retrieval evaluation, right? Mm-hmm. What would you? So yeah, can you describe what they do here?
Yeah, so here they consider both what they call the closed setting and the pooled setting. Closed just means the documents that came with the data set. Pooled means also including documents from the other data sets in.
Okay. So I guess the hope here is that you want to show that if you include the task in the query, you have these task instructions, you're gonna get less of a hurt, like there's less of a hit in performance once you kind of have all these destructor documents that you said.
Yeah, exactly. So for example, Code SearchNet Python CSP, the last data set here, code is the document. So you'd expect, even if these are included from the instructions, you should be able to filter out code easily because the other queries are just not looking for code.
Yeah,
that's the hope.
And do you think that they fulfill this, or they kind of live up to this hope?
It's hard to say. I mean, the results are very different depending on the data set and the method you look at. So if we look at the average, for example, we can say things like pooled is definitely harder than closed.
Yeah.
If you look at the pooled metrics, they're always lower. Whether that's harder because of confusing models or because of new relevance, I don't know. Mm-hmm. If you look at the code search, there's not much difference often between closed and pooled.
Yeah. Yeah, I guess that, I mean, my kind of general sense when I looked at these was like hopefully you see kind of a trend, like some data sets seems to be kind of quite harder than others in terms of like the hit. So like I guess what I'm trying to say is like the inter data set difference is higher than the inter models difference. So that to me kind of makes the hypothesis kind of a bit weaker. That the task awareness truly improves a lot. I mean, if you look at the aggregate here, right on the rightmost side, you do see that TART dual is the one that has the least average drop in performance. But if you go into kind of like some of the data sets, it still does get quite a big hit in performance in some of them. And
that's interesting. I guess it's the least drop, but also less effective than the cross encoder, right? Because you could say, I think the cross encoder would be more robust to this two settings, but also the cross encoder performs a bit better. So this is tangled up in this understanding of the drop, right?
Yeah.
I guess you can say...
So I guess you could kind of like frame it as like there's less merit to a small drop if the performance to begin with was less strong, right? So then you have these two kind of effects that are a bit entangled if you only look at the delta, right?
I guess you could say, for example, if you look at Contriever with re-ranking, it's a bigger drop than any of their cross-encoders and their re-rankers. Or if you look at Contriever, the bi-encoder against TART bi-encoder, the Contriever again has a bigger drop. So maybe you can say, between comparing family to family, baseline versus TART, TART has a smaller drop than the baseline does. Right? A drop of 9 with Contriever versus 7 with TART bi-encoder configurations. A drop of Contriever re-ranking 13 versus up to 10 with cross-encoder with TART cross-encoder. Yeah, I think it's an interesting evaluation setup, but I guess what I'm showing here is I don't know exactly how to interpret all of this.
I'm also finding it hard to get like a good sort of takeaway message from these results.
And I mean, we're comparing averages against averages, right? Within each of these data sets, there's a query distribution.
Yeah.
Some are hurt more, some are hurt less.
Yeah, right. I guess it's a very good, like looking at average, I guess like you need to sort of condense things into one number at the end of the day to claim that your model is the best. But you probably find much more relevant information if you look at some of the individual results and dive deeper into that.
Yeah, I mean, it's when you see such big drops, so like 78 to 58 on WikiQA, that's really interesting. I wonder exactly what documents are being retrieved. Are these mostly documents from ambiguous QA or from all data sets? Or I don't know. Like, this is something that would be interesting to look at. Where do the mistakes come from?
Yeah. Anyway, I think that's most that we can distill from these results. So if we move on to in the ablation section, so they have a couple of they have this section 8 on ablations. It didn't seem to me like many of these ablations were showed like extremely strong sort of results that kind of hint that something is particularly relevant of their method. Is there anything you'd like to highlight from these ablations as the most, I don't know, informative?
There are a few small interesting things. So for example, looking at task diversity, I think that's figure 7. So they pointed out, for example, if you look at the QA only configuration, so these are the middle bars, it doesn't do well on Arguana, which is, not about QA only, for example. Mm-hmm. There are little observations like that, I think, that make sense. But as far as a big, like, overarching observation, I don't have anything to point to.
Okay, so then I guess we can just move on to the sort of last wrapping up section, basically. So I guess the first thing that I wanted to comment on, we've already hinted, is how strong do you think these results are, or how would you qualify them?
I'm not sure if they're state of the art, but it shows an interesting way to improve, and I like that it's principled in the sense of they're thinking about what a task is, what is it, like unit, intent, and domain, and they kind of break things along these lines. I really like that idea of trying to think about how different data sets relate to each other across multiple dimensions, and maybe trying to train in a way that you can learn about this, right? So maybe you have combinations that you evaluate on that weren't seen during training. I assume that happens. Mm-hmm. If you had a comprehensive enough way of thinking about different types of intents and so on, maybe you could get pretty far. There's a lot of work, for example, doing weak supervision for query intent classification. Right? Okay. What happens if you start plugging things like that into here? I don't know, but
because something we haven't discussed that much is the whole aspect of user modeling of these, right? Because basically, this paper is only concerned about the data set part of things. But if you're thinking about, okay, you're building some model that's deployed somewhere and like users are gonna use it, intent is gonna be implicit in a lot of queries, right? And you want your model to somehow understand that, so that it can surface the most relevant documents, right? And that is very much user dependent. Right, so like if you're doing a search and I'm doing a search, we might have different preferences for what we are looking for when we're searching for a Python something or like our previous. So what is there anything you see kind of at these kind of merging to these two things of user, like what is interesting that is happening right now in the user modeling side of things that could sort of be used and in building data sets or
Yeah, I think it's interesting to think of from a user modeling perspective. I'm not sure exactly how we would incorporate the user model immediately, right? So like Python is an interesting example. Maybe you mean Python code, and based on my previous searches, I'm a zookeeper, right? It's a very different Python, right? So if we had information like that, this is kind of like a distribution over topics. So it's a bit different than could be easily incorporated with instructions like this, but maybe there is some reason to, some way to incorporate it, right? This paper doesn't tackle that at all. It's a different problem, but I think it certainly could be. I think the intent is there, whether the model is explicitly aware of it or not. So you can just kind of try to handle intents by default, make the model do something reasonable. Most people in the data mean Python code, so that's what's going to happen. You can try to do like diversification. There used to be a lot of research in this in the IR community where you know there are different types of Python and you try to balance this out in your results.
I see.
Or here you can explicitly handle intent, which I think is a cool idea that would have been much harder to do without this sort of neural machinery, where you're asking the user to give some description of what their intent is, and then that will return better results.
Right. And I guess this whole idea of explicit intent modeling can be also helpful in the space of conversational information retrieval, where a model can kind of like ask follow-up questions to narrow down these intents, right?
Yeah, that's interesting also. So I don't know if these intents map easily to that domain, but you could come up with other intents that definitely do, right? So you could think of conversational answering, question answering, giving a fact back to a question, or giving some historical context, or all sorts of things.
I guess one of the problems that I see with all of this is like the more aspects you incorporate, the more realistic the setting becomes, but at the same time, the harder it is to measure on a standardized benchmark, right? Which is something that research is very concerned with, kind of being able to make measurable progress. So, I don't know. Do you think that's something that can be breached, or as in like the current benchmarks, as in task intent is very much not a first-class citizen in most benchmarks that are popular in IR. Do you see a path to having more of that kind of baked into the benchmarks?
Yeah, I think it's definitely possible. I mean, with their like high-level task type intent, this is not so hard to do. If relevance judgments are being collected already, if it's useful, we could have a query, placed into an intent hierarchy somewhere. This also requires knowing that intent hierarchy of different, intents that could exist.
Yeah.
To me, it's more of a problem of how to design things rather than like the labeling effort. Because if you're already doing relevance labeling, I don't think it's that much work to think about what the query intent should be. It's just a question of is this something we want, and if so, how do we get it in the smoothest way possible? And this is also not a bad situation to use like weak supervision and all sorts of classifiers for, right?
What is weak in this context? What is weak supervision?
So you could have like an intent classifier that you didn't train with a lot of data. Right, so like navigational intents are probably not that hard to find. Maybe that's not even an interesting one, but just as an example, if you're looking for a website, well, there's some cues there. Maybe you included the .com or .net or something even.
Yeah.
Right, so you can have like classifiers trained on not a lot of data that are then used to label queries as a kind of a weak label. There was work like this, fairly recently. Orcas is a large data set, and there's some Arjen de Vrij, his group, from Radboud. They looked at basically predicting intents for all these queries.
Okay.
I think I may be misremembering.
In terms of future work in this space, what do you think is what would you bet on is like an interesting or sort of more obvious next step to build on task-aware retrieval?
Yeah, so one possibility is looking at multiple intents at once, right? So you have this hierarchy. You could think about exactly what they're looking for when they're looking for an answer, right? Are they looking for a factoid like a year, or are they looking for some more like essay type answer to have an understanding of why this is the case it is, right? So this would go under one type of intent they have, but this requires query specific information. Maybe there are other ways to combine the intent with the query. What they did seems very reasonable, but this paper wasn't really about architectures or how you model it, right? Maybe there are other ways. You can imagine like having embeddings for different types of a domain and task and stuff. I'm not at all convinced that's better. But if you're not using a decoder, I don't know what impact that has versus prompting.
And in terms of, like you said, in terms of optimization, what is your sense of, so say in the table 3 that we've seen, we have sort of different camps of optimization. Let's say if you could make an ensemble of everything, or like have kind of the current best recipe for training some cross encoders or like re-rankers that perform very well in zero-shot setting or out of domain. Do you think this is sort of should be part of like the recipe going forward in this sort of?
Should this task awareness be part of the recipe?
Exactly. Like, would you expect this to become a new norm when you're training cross encoders? Yeah, or.
I suppose, if you're training cross encoders, it clearly helps here. I was expecting it to help more. I mean, it does clearly help. It's definitely an improvement. I'm not criticizing that part at all.
Yeah.
But I thought that having knowledge of what these BEIR datasets were getting at would improve more. My feeling is kind of there must be some way to push things further, or maybe there's some hidden difficulties that are not.
I mean,
so obvious.
one thing that I guess makes me think is the issue of scale, right? So it does seem like the more you add to the query, the more this becomes a kind of like natural language understanding type of. So like the line between natural language understanding and information retrieval kind of gets blurred, right? Because you just feed this whole thing into a model. And I guess like I would have an intuition that there might be some kind of phase transition in scale, a little bit like you've seen with a lot of this large language modeling research, where like once you go into the 100 billion range or something, you suddenly see this huge jump in zero or few shot performance. So I don't know, I don't know if you would agree with it, but I feel like it very well might be the case that this thing doesn't really help at this scale. But if you're looking at models that are 100 billion parameters, like these massive models, this task awareness kind of suddenly becomes a deal breaker. Or
I think that's a good point. As you have a larger model, I would expect it to be able to parse that task input and match it a lot better, right? So GPT with task instructions is GPT-3 is different than T5, right? And here, like T0, for example, is the encoder part of T5, roughly. So maybe I think this is an interesting perspective, right? Maybe it's helping a little bit with these smaller models, and you'll be able to make much better use out of this task-aware information as you have a bigger model.
Do you see? I mean, I guess that's a bit of a bittersweet point because as NLP models have grown quite a lot in IR, still the state of the art is not so. It's not so massive. I mean, it's definitely very big, but it's still kind of manageable sizes. Do you kind of, what do you see in the future of neural IR sort of be in this scale kind of perspective?
Yeah, maybe we'll see bigger improvements with scale than we have, but I think part of it is that everyone is scaling decoders, which are just not. I mean, I'm not aware of a work that creates very like state-of-the-art bi-encoder representations from a decoder. So here they have encoder-decoder stack, and they use only the encoder part. Well, GPT-3 is decoder only. So maybe part of it is there's no place to cut GPT-3 off such that you have a representation that could be used as a bi-encoder. So there's work producing embeddings from it, which works fine, but as far as I've seen, this isn't bringing anywhere near the same improvements that GPT-3 does compared to like T5 for NLP.
All right. I think that's a good point to end. Do you have any other sort of points or things you'd like to highlight?
No, I think it's an interesting work. I'm glad people looking into the tasks, and I like this decomposition of how different parts of a task affect things. And this BERRI seems like a nice resource to have. So
it seems to me like quite great. I mean, you have a bit of more the historical context here, but it does seem to me like the sort of transition to out of domain benchmarking, or like this kind of like benchmarking on a broad range of data sets instead of like a single one. It seems to me like in information retrieval has happened quite fast, and I think that's kind of like really cool to see. Like it feels like 3 or 4 years ago, it wasn't that common to have such kind of awareness of how, I don't know, testing a broad range of data sets. Yeah,
no, it is a nice trend. I think people realized that while this wasn't an issue with BM25, now it definitely is an issue. And so we need to, rethink a bit how we're reporting results here, because these models have issues that BM25 wouldn't, or, many previous approaches wouldn't move between domains. Right. So it's really highlighting these shortcomings.
Yeah, which I guess kind of like goes back to this point I think we've made before of like, how much is hidden in the qualitative analysis of the results, as in like you might have the same number at the aggregate, right? But at the kind of behavior, or like once you kind of go to different data sets, you might have very different problems. So that's very important.
Yeah, exactly. Yeah.
All right. I think that's a really good place to end it. Thank you for watching and listening, and we'll see you in the next episode.
Great.